So yeah, thanks for letting me present at the meeting today. I'm um, excited to share this work, and it's a great presentation by Jan, so I can follow on with a lot of the stuff he's talked about. And want to thank Matt Shoup, who's contributed a lot to this analysis and presentation, as well as the other folks listed at the bottom of this slide. I'll be focusing on the surface energy budget and the process of relationships between the different terms, specifically at Summit Station, and kind of taking a more detailed approach using the observations that we've been fortunate enough to take up there. And not to beleaguer the importance of the Greenland Ice Sheet, but just an overview about how it's contributing to sea level rise across the globe, freshwater, with implications for freshwater input into regional oceans. And kind of piggyback off of Jan's slide, I have a kind of the early 21st century plot on the upper left-hand part of this slide, where we have the cumulative mass change. And again, it's been decreasing in the early part of the 21st century, and about 50% due to the ice discharge and 50% due to the surface mass processes, with increasing amount of mass loss due to those surface melt processes towards kind of 2010 and beyond time period. And so part of the reason for that is increases in surface temperatures. It's estimated about half a degree per decade across the Greenland Ice Sheet, with estimates higher at Summit Station up to about 0.9 degrees per decade. And so these increasing surface temperatures have implications for the maximum melt extent. So how much how much of the surface is melting, at least for a couple days during the summer, is shown by this bottom right plot. And you can see an increase during the same time frame, but there is quite a bit of variability in the melt extent. And so, what's driving that is, as you get closer to that 0 degree threshold, the variability of the surface temperature plays an important role in determining whether you reach that melting point. So what I'll be focusing on is kind of the drivers of that surface energy budget. And been fortunate enough to have a kind of a confluence of measurements for a time period up at Summit Station. And Summit Station's close to this red dot indicated by the map up to the right-hand plot of Greenland there. And ICECAPS is able to measure the atmospheric state and cloud properties above the ice sheet. We also have broadband radiation measurements, able to measure the upwelling and downwelling shortwave and longwave components of the surface energy budget. Those are made by the Swiss Federal Institute, as well as NOAA GMD. And then David Noon's project has some nice measurements on this 50-meter tower, subsurface temperatures, as well as 10 and 2-meter wind, humidity, and temperature, with some overlapping measurements, again, by NOAA GMD. So these high-quality measurements, you can derive the turbulent heat fluxes as well as the ground heat fluxes from those subsurface temperatures. And at Summit Station, we can kind of think about what's going on in the accumulation zone without the energetic influence of kind of the melt processes, the phase change term. And so thinking about what's driving the surface energy budget and how the surface temperatures respond. So getting into some of the results, we have this annual cycle of the surface energy budget. And the year we have all the components is July 2013 to June 2014, indicated by the solid lines in this plot. And then for some of the components, we have data dating back to 2011, just kind of give you an idea of how representative that 1 year might be in these monthly mean plots. You can look at the different components. The negative value is cooling the surface, a positive value is warming the surface. So radiatively cooling during the winter months, and then we get an increase into June and July where it's actually positive for the total radiation. Sensible heat flux is anti-correlated to that total radiation, in that you get a warming of the sensible heat flux during those winter months, and then a decrease into the summer. Latent heat flux monthly mean values are relatively small, slight cooling in the June and July, warming throughout the other parts of the year, and then subsurface heat flux cooling in the late spring, early summer, with warming during much of the rest of the year. And then the numbers at the top of this plot indicate the residuals of all these monthly values. And so you can see we're getting fairly decent closure of the surface energy budget from all these independently measured components. So to think about kind of what's driving the variability of this of the surface energy budget, and Jan talked about this and did a nice job at introducing it in the previous talk, is the cloud radiative forcing effect, basically an estimate of the cloud's impact on the radiative flux of the surface. So thinking about, you know, the measured radiation versus what would the radiation be under equivalent clear sky scene. And you can see the box and whisker plots representing the statistics for a given month. And really, especially on average, the clouds radially warm the surface in all the months, where the long wave warming effect is due to the highly emissive clouds, especially compared to a clear sky scene. So warming in the long wave part of the spectrum, and then the clouds are cooling in the short wave part of the spectrum. But although they're reflecting the short wave, the surface is already has a high albedo, so it's even under clear sky scenes, it's reflecting a lot of the short wave part of the spectrum. So we have really clouds warming the surface again throughout the year with we've calculated the annual average of about 33 watts per meter squared at Summit Station. So another way to think about this is to think about liquid water clouds. So we have liquid water paths shown in the y-axis, and once you get to about 30 grams per meter squared, these clouds become opaque in the long wave. And so this really increases the downwelling long wave radiation. But another thing that can drive the surface temperatures is the net shortwave radiation. So we've shown times when we have sun and no sun, sun being in red and no sun being in blue. And so you can see we get an increase in the downwelling long wave plus the net shortwave radiation, which we're defining as the forcing terms. And this can be either due to the presence of clouds, sun, or a combination of the two. And what's evident in the panel to the right is you get an increase in the surface temperatures, which is what we've expected. But one way to quantify how much the surface temperature is responding to this forcing is to think about the response of the long wave upturn. And so long wave up is proportional to the surface temperature to the fourth power. And so you see the increase in the surface temperature, you'll see the increase in the long wave up. And then we also want to investigate how the turbulent and ground heat fluxes will modulate this warming. And so we can look at the scatter plots of these various terms throughout for this 1 year data set that we have. And here in the top panel A here, we have the forcing terms in the x-axis and the response terms in the y-axis, a nice -1 slope indicating surfaces radially driven, and we have nice closure for all these terms again. So as you get an increase in the forcing, you get a corresponding response of the rest of the surface energy budget terms, and then you can break this up into the different components, and you see again an increase in the long wave up shown by panel B, and then a decrease in conductive heat flux, sensible heat flux about -0.1, decrease in the slope for this, at least on the annual cycle scatter plots, and then a smaller decrease from the latent heat flux. And you could split this up into different seasons, just showing kind of a representative slopes for different parts of the year, where yellow might be parts of the year where you have no shortwave radiation, sun's below the horizon. You get this steeper slope than during the summer, where you have the shallower response, or a shallow response of the long wave up. And you could do this for every month and kind of plot the annual cycle of how these different terms respond to changes in the radiative forcing. And that's what we're showing in this plot. Again, the long wave up being the largest response, kind of dips down into the summer, stronger response in the winter compared to the summer. You get an increase in the latent heat response, shown in the green, compared to a small response in the winter time. It's interesting that the sensible heat flux is relatively constant throughout the annual cycle. And then the second largest response is the ground heat flux response, where it's about 30% in the winter, and then it drops into those summer months. And so you can think about using these process relationships to evaluate either reanalysis or models, and we've done this for, let's see, ERE interim, and here I'll be focusing on the community Earth system model, which Jan introduced before. State of the art climate model. Here, Jan's been gracious enough to provide these 5 years of data representative of the current climate. So trying to evaluate how this current beta 7 version is performing, and it's basically a candidate for CSM2, which will be officially released possibly later this year. And but it just, I guess for this talk, it's illustrating a way to evaluate this model and to kind of show some of the strides that they've made in representing some of the forcing terms from that previous version of CSM that was released, where they didn't have very many liquid bearing clouds. So if we look at the two perspectives, the forcing and the response, you can see the comparison of CSM shown by the red box and whisker plots and the observations in the black. You see a nice comparison of the forcing terms between those box and whisker statistics. And then we get a fairly decent representation of liquid bearing clouds, or the liquid water path, shown in the bottom panel. And so a more accurate representation of those will really improve the forcing comparisons. But I guess the next question would be, how would the other terms respond to these changes and improvements in the forcing, and how will the surface temperature respond to changes in these forcing terms? And so looking at the process-based relationships and the various responses of these terms, you see the observations again are in the solid lines, and now we have the model in the dashed lines. You see that the long wave up response, kind of a proxy for the surface temperature response, is lower than what we're seeing in the observations. This could be due to kind of an over response of the turbulent heat fluxes. We have a high response of the long wave up. I mean the latent heat response in the summertime, shown in green, and then really throughout the annual cycle, the sensible heat flux response seems to be larger than what we've seen in the observations. This model seems to do well with the ground heat flux response, as you see in this coupled climate model. Good comparisons between the ground heat flux response, with maybe a little bit higher than what we see in the observations during those summer months. And so just to kind of summarize, we've quantified the impact of clouds on the surface radiation, coming up with 33 watts per meter squared for the annual cycle. But those results can and have been used to evaluate some of the previous studies, that satellite perspectives, and obviously can be used to evaluate the model as well. And then we've used basically discerned how the coupled ice sheet interactions, how the system adjusts to changes in this forcing. And so we've come up with the estimates of the surface energy budget to relate, the forcing terms to the response terms to provide a framework to evaluate either reanalysis or the global climate models. So as the global climate models need to really represent the physical processes that are happening, as they project what could happen in these future warming scenarios. You want to make sure made some good strides in representing the cloud processes, but you also want to be able to capture the process-based relationships and how the interaction between the atmosphere and the ice sheet will result in accurate surface temperature variability. So yeah, thanks to the National Science Foundation as well as these other folks who've contributed to the observations. And yeah, welcome any questions. Thanks.
Thanks, Nate. Very interesting. Do we have questions for Nate? Well, I'll start off with a question again. You call for an improved representation of models, and you've characterized process relationships seasonally. That has some cloud. But I'm wondering if I'm sorry to get here. I'm wondering if there's a finer analysis of regimes that, following up on Jan's comment in his presentation, that we need to understand cloud regimes. Is there a way that we can do a finer analysis of cloud regimes here and how they dictate these physical relationships?
Yeah, I think I heard most of your question. I mean, as far as cloud regimes, you mean as far as ice water clouds versus liquid water clouds?
Yeah, or mixtures and heights and.
Yeah, I mean the analysis here was kind of a well, I guess there's two ways. I mean, I guess the strength of the way that I've looked at it is that the responses should be responding to the forcing kind of in a similar way. So by looking at the responses, you've maybe taken out of the equation how the atmospheric processes have modulated the downwelling radiation. So you're just looking at changes in the forcing radiation that's reaching the surface and how those the surface temperature is going to respond to that, because it is, I mean, that's a big area that needs improvement, and Matt's worked on that a lot, and other folks have, it's really tough to represent the microphysical processes that are going on in the clouds, especially since these super cooled liquid clouds can occur down to about minus 40 degrees C. So I guess looking at this perspective, you could use, the ICECAP measurements to really evaluate what's going on in the atmosphere, because they're able to resolve a lot of the microphysical processes and you know, the cloud radar and various instruments, but looking at the surface energy budget process, you can kind of isolate what radiation is reaching the surface, how the surface temperatures kind of should respond, if that makes sense.
Yeah, definitely. Thank you. Do we have any more questions for Nate?